Let's move on to Module 13D. We'll be talking about radioactivity. Quite a bit of vocabulary in this module. Radioactivity, radioactive isotopes, radioactive decay, beta decay, daughter products, beta particles, alpha decay, alpha particles, gamma decay, and gamma particles. The weak force is another aspect of the electromagnetic force. Because of this, most scientists consider that there are only 3 forces instead of 4. As a review, there's the gravitational force, the strong force, the electromagnetic force, and the weak force put together are called the electroweak force. However, one thing that's different about the weak force is it governs a portion of radioactive forces. Radioactivity is the result of atoms called radioactive isotopes. A radioactive isotope is an atom with a nucleus that's not stable. So to become stable, the nucleus must decay, and this process is called radioactive decay. Radioactive decay can appear in several forms. Let's begin with beta decay. In beta decay, the nucleus changes one of its neutrons into a proton. Then the neutron emits an electron. The negative neutron gets rid of a negative charge, and the neutron then becomes positively charged and becomes a proton. In beta decay, the electron produced is called a beta particle. It's still an electron, but they just name it a beta particle. So here's an example. We have a uranium isotope, U-239. It has 92 protons, consequently 92 electrons. And if we subtract the protons from the mass of 239, there are 147 neutrons. This nucleus is unstable because it contains too many neutrons. So to stabilize, a neutron changes into a proton by emitting an electron or a beta particle. The nucleus will now have 93 protons instead of 92. An atom with a nucleus of 93 protons is no longer an isotope of uranium. If we look at the chart states that the atoms with 93 protons are actually called neptunium, atomic symbol Np. And so when U-239 goes through beta decay, it becomes Np-239 or neptunium-239. In physics, U-239 is called the radioactive isotope, and Np-239 is called the daughter product. So essentially, the isotope has given birth. The electron released from the beta decay, once again, is called the beta particle. Now the second form of radioactive decay is alpha decay. Instead of emitting beta particles, some isotopes emit alpha particles. An alpha particle is actually a small nucleus that contains 2 protons and 2 neutrons. So you could think of this as essentially a helium atom, because a helium atom has 2 protons and 2 neutrons. So for the radioactive decay of alpha decay is actually the emission of a helium atom. Here's an example. If we have a polonium isotope, polonium-214, it has 84 protons and 92, scratch that 92 and I just fixed it. It has 84 protons and 84 electrons. The mass, the atomic mass number of 209 minus the 84 protons means that there are 125 neutrons. This nucleus is so unstable that it actually emits a helium atom, or 2 protons and 2 neutrons. The result is 84 minus 2 leaves us with 82 protons. If you look at the chart, the atom that has 82 protons is polonium. And polonium has an atomic symbol of Pb. So the mass number of the lead daughter product is 4 less, 2 protons and 2 neutrons less, and becomes 210 Pb. We originally had 214 Po, now we have 4 less in the nucleus, so we have 210 Pp. Your text has this figure 13.5, which gives a description, and it shows a radioactive isotope. We have protons and neutrons in the nucleus, and a beta particle is emitted, and with that beta particle being emitted, which is an electron, the daughter product has 1 fewer neutron and 1 more proton. So the unstable nucleus reduces its number of neutrons, increases its number of protons by ejecting an electron or beta particle. It also ejects an antineutrino, but this is a particle that is just too complicated to learn about in high school physical science, so we won't be talking about it. Here's another radioactive isotope, and it's got alpha decay. So in alpha decay, it emits a particle of helium, an atom of helium, which is, remember, 2 protons and 2 neutrons. So the daughter product, with 2 fewer neutrons and 2 fewer protons, is pictured right here. The last form of radioactive decay is gamma decay. In gamma decay, a radioactive isotope becomes stable by emitting a gamma ray. Gamma rays are light. So a gamma ray is essentially a high energy proton. When going through gamma ray decay, the isotope does not change its identity. So with our 3 kinds of decay, with beta decay, an electron is emitted. With alpha decay, 2 protons and 2 neutrons are emitted, and gamma decay, a gamma ray is emitted. Let's look at an example of gamma decay. We have a thorium isotope. It's thorium-229. It has 90 protons and 90 electrons. It has an atomic mass of 229. If you take that mass and subtract the 90 protons, that leaves us with 139 neutrons. Gamma rays are emitted because the nucleus has too much energy. The isotope still has the same amount of protons, neutrons, and electrons, but less energy when gamma rays are released. There are 3 examples in your text, so let's go through each one. This one will be for alpha decay. They want to know, with thorium-232, what is its daughter product? Well, thorium has an atomic number of 90, so 90 protons and electrons. The mass is 232 minus the 90 protons, which gives us 142 neutrons. The daughter product will have 2 protons and 2 neutrons less than thorium. So 90 minus 2 will be 88. And that will leave us with 4 less in our nucleus. So we're going from 232 thorium to 228. And we have 88 protons. All atoms with 88 protons are called Ra, which is radium. So now we have radium-228 as the daughter product as a consequence of alpha decay. The last example is about gamma decay. And we have Y90. Because gamma decay simply deprives the nucleus of energy in the form of light, it doesn't change the nucleus. So the daughter product will remain as Y90. So if you have any questions, be sure to contact me. Move on to your own problems, and we'll speak again in the next video.